Okay, I want to continue on with this last problem we just did in adding vector components in part 1, and we're going to make this part 2. I don't know why I didn't change that, but we're going to see if we can make that go away. Make that a 2. Cool. Okay, so we had vector A, B, and C in this particular problem. And what I want to introduce you to is a way to organize this. And I'm a visual learner myself, and I like to see things in tables and diagrams to make all this make sense. So let's do this. We're going to do force. Okay. I'm going to do the magnitude. And that's going to be in newtons. Then I'm going to do the x components. And that's in newtons. And then we're going to do the y components. And those are in newtons. Okay. And we're going to be able to sum all these up so you can see how the addition goes and what makes sense, what doesn't make sense. All right, so we had force A, vector A, which was 800 newtons, and magnitude, it means it just has a number. I don't have a negative sign or anything on this. Don't worry about it. From part 1, we determined the x component to be 640, and I'm not going to put the newtons in there. It's up in the top up here. You could if you wanted to, but why clutter up the scene? And the y component for vector A was negative 480, or plus 480, not negative. Okay? And then B was 424 newtons, and I had an x component for that as negative 224, and a y component of a negative 360. Okay? And then we go down to vector C, or the force on vector C, and it was 408. And I'm doing newtons all the way up and down that one, so I'm going to be consistent even though I don't have to because I put it up in the table. Good engineering format, and I'm violating it. The x component is 192, and the y component was negative 360 again. Okay? Now, if I look for r of x, basically I'm going to sum that, and r of y is the sum of that column. Okay? So when I get all done, I should wind up with 608, and over here I'm going to wind up with negative 240. Okay? So that helps you give an image to what's going on with the vectors up here. So someplace in this, if I was to lay this out, we're going to get a vector that's going to go someplace out into there. Okay? And that's going to be my r. Okay? But now let's go do the math. Okay? So write it out, and in your actual engineering format, you don't have to write this out, but write r, so this part you do, but the right you don't have to. R of x I plus r of y j. Okay? Now, remember the I and the j, and then eventually in three-dimensional k, gives us the magnitude and the direction. So we got a magnitude in x and the magnitude in y, but now we get the direction because we know where we are in the planes. Okay? So vector planes. All right, so if I take this and I write this out in terms of this, so 608 newtons times I plus negative 240 newtons J, all right, and then rewrite that. Now, you could skip the second step here, but my advice is this. I spent a lot of time in my bachelor's degree chasing around negative signs for no apparent reason because I'd lose track of them. So to me, it's always better to keep track of them and know where they are before you do something horrible that you regret later. Okay, so that is the vector of R with its components, and that'll define that. Now, we need to do a little bit more to this to make some sense out of it, and I'm going to cheat right here. I'm not going to use a ruler. See if I can do a good freehand sketch. Not bad. Okay, so there's my X, my Y, and this vector is going to go out someplace in here. That doesn't look so good. Still doesn't look good. All right. It's going someplace out in here. All right. Get up there. And that is my vector R. Okay. Which I know to be equal to 608 newtons in the I minus 240 newtons in the J. Okay. Well, in order to really define that, we need an alpha, and we're going to do this. All right. So find alpha. Okay. Well, that's the tangent of alpha equal to R sub y j over R sub x I, or opposite over adjacent if you go back to basic trig. Okay? All right, so we plug some numbers in here. We got negative 240 newtons divided by 608 newtons. And at this point, you can drop the j and the I, and we're really good at this. And if we solve for the tangent of alpha and get this in its decimal form, we're going to find out it's negative 0.3947. I guess I don't need the ruler anymore. Get that out of the picture. All right. Bragging on my age, I guess. There was a time I remember as a student where we actually had to go to trig tables to look up that number to find out what alpha was. Okay. You nowadays really just have to do this. Alpha is equal to the arctangent, all right, of negative 0.3947, and you're going to find out that alpha is equal to negative 21.54 degrees. And that gives us our vector, our magnitude, and our velocity, or not our velocity, our direction. Okay? All right, so that's a follow-up to part one, but trying to make some sense out of this so you can get some hang of what this all means. But when we talk about adding vector components, it's really think of it in a table form, but writing it out in a mathematical equation. Okay? However it makes you see it, try it. If you're not sure, somebody's figured it out. Go take a look at it and see what happens. Okay? Now, we need to go figure out one last bit here, and that is what is the magnitude of R? Okay? All right, so if we take a look at this, we know some things now, which we didn't know before. We now have an alpha. So we have an alpha of negative 21.54 degrees, okay, which we didn't know in the beginning. But we also know that we have a component and we can actually solve for some of this. All right. So in doing this, let's do this. I think what I need to do is come back to this angle up here. So if we want to know this, we know the x component was the 608 newtons, okay? And we know the angle, then we're looking at the cosine, or if we want to do the y, and we know this alpha, then we're looking at the sine. So either one will work. I'm going to do sine just because sine's easier to play with in my world. I don't know why. We're going to do r is equal to negative 240. Negative 240 newtons divided by the sine of negative 21.54 degrees. Okay, and where'd my calculator go? I lost my calculator. And R turns out to be 653.68 newtons. And if someone hasn't explained this in the world of engineering, we're going to call that 654 newtons because we're looking for three significant figures most of the time. Okay, and my logic is this, and take it for what it's worth. But is there much of a difference in 653.68 or 654 when I'm calculating stresses down the road on designs where things are in the tens of thousands to hundred thousands of pascals, or if it's in the English system in pounds per square inch? No. So rounding to three significant figures, 654 makes sense. Cool. All right, so we've actually found more than just adding the components. We've actually solved for the whole problem of knowing where this force is. Now, the interesting thing is, take you into a little wander into the future so you can see what things are going on here. Let's say this is a shaft, and I have it like so, and we'll just cut it off the back here. All right, this is Z, that's Y, that's X, and for some reason I have a resultant vector out here that is R is equal to 654 newtons, and my alpha is equal to negative 21.54 degrees. I have a force that is now going to act on this shaft, and I'm going to need it in the X component. I'm going to need it in the Y component, because in the Y component, if I draw this this way, my Y component is going to have a force that goes this way, R sub Y, and that'll be whatever that turned out to be. All right, and what really happens here is I'm causing this thing to bend like so. Okay, and then if I have my X component, let's go back to black. I have my X component here, and it's tugging it that way. Okay, so this is Y, and Z is coming straight out, and I guess I should have done Y, Z, and this is my X direction. What's really happening here is I am bending this thing over to here. I guess a better view of that would have been this. Let's do it down here. This was my shaft, and I'm basically bending it to the right here. Okay, and I need to know all that. I need to be able to down the road in strength of materials. You'll find out about Moore's circle, which is combined stresses, and that'll help us resolve things stress-wise, and the world's a happy place. Cool. All right, I'll give you some problems related to this to give a try. If you got questions, ask. Otherwise, I'll catch you in the next video. Bye.